Hi, everybody, welcome back to the NYSE. My name is Dave Vellante. I'm here with a special guest, good friend of theCUBE, Jim McNiel, who is the Chief Growth Officer at TAE Technologies, a company that does nuclear fusion technology. You might be familiar with Jim. Awesome to see you again.
Good to see you,
Thanks
David.
for coming down here.
It's a pleasure.
When was the last time you were here?
It's been too long. You mean here or on theCUBE?
On theCUBE, both. That's been a real long time. You've probably been here.
I've been here before.
Before you came
then.
back to theCUBE.
Yeah, everything's changing.
So you've had such an interesting career, and you're now in a company that is really positioning for the future. Let's start with TAE and nuclear fusion. What do you guys do?
Well, TAE is really the first privately funded, fusion company dedicated to developing the cleanest possible energy solution on the planet. So what fusion is really good for is turning atoms into energy. You remember E equals MC squared, you got energy on one side, you got mass on the other. Well, we're about tapping into those atoms, converting that mass into energy. That's the way our sun works. Every star in our solar system is a fusion reactor. How do we replicate that star here on Earth so we can have abundant carbon-free energy without radioactive waste?
Right, and so fusion will use hydrogen, sometimes other gases like boron?
There's a number of different ways of doing it. There's primarily 3 different fuel choices. They all use hydrogen, as you pointed out. The other options are a form of hydrogen which is deuterium and tritium. That's one primary fuel source. Another one is helium-3 and deuterium. And a third is hydrogen and boron. Okay. And they all have their pros and cons.
And we can, if we have time, maybe we get into that, but there's a lot of confusion between fusion and fission. Now, fission uses radioactive material, right, uranium. Explain the basic difference for the audience.
Fission uses highly radioactive materials because they're unstable and they're easy to split. So when you split an atom, you're releasing a tremendous amount of energy. And so there's 2 types of fission. There's uncontrolled fission and there's controlled fission. Controlled fission is what we have in a nuclear power plant. Based on the fuel rods and where they are and what activity is going on in the reactor, we can determine the amount of heat being generated by these atoms being split by neutrons. When they split, they fly off and hit another atom.
Create
which
energy.
Splits and fly off, hits another atom. So it's a chain reaction, which is why if you don't control it, it can explode and be a great massive energy at one time, like an atomic bomb.
And with fission,
with fusion,
with fusion, you're heating up the element, correct? With a lighter gas?
Fusion is by nature the exact opposite of fission. It's taking 2 atoms and merging them together and then creating new atoms. So it's the way all matter in our universe has been created in star factories. So all of us, all the atoms in our body have come ultimately from a star at some point in time. Stars fusing elements together and forming carbon and helium and hydrogen and everything.
We're stardust.
Yeah, we're all stardust,
Okay.
right? So when you fuse things together, like in the case when you fuse boron and hydrogen, you get 3 alpha particles of helium. So you're producing an inert gas that can be released in the atmosphere and there's no harm. It's not radioactive, it just floats up into the atmosphere. You can blow up balloons with it. When you're fusing deuterium and tritium, you're actually producing neutrons. Neutrons are radioactive, they're highly energetic, and whatever they touch, they impart that radioactivity to that. So the fusion companies that are working with deuterium and tritium have a couple of big challenges. One is, where do you get the tritium? It doesn't exist naturally on Earth, you have to create it. And number 2, how do you deal with the neutrons? And then the other form, deuterium and helium-3, same problem. Where do you get helium-3? It exists on the moon, a few parts per 10 billion parts. You could scrape it off the top of the moon, but it doesn't really exist here on the planet. So the only way you create it is by waiting for tritium to decay, which takes 12 years, or making a new fusion reactor, fusing deuterium and deuterium to create tritium fuel. So that's why I'm very biased that the best way to get to a working fusion power plant is to use boron, because it's mined by the metric ton in the California desert. Okay. It exists everywhere around the planet. It's pennies a pound. And you can put a lifetime supply of fuel in the parking lot of a fusion plant.
And people sometimes, you get confused. It is nuclear fusion, it's nuclear. People think it's radioactive, but it's not. It's nuclear because you're operating on the nuclei
The nucleus
of the atom.
You're down there penetrating. When you have you have molecular changes where matter stays the same. If you put 10 grams of vinegar and 10 grams of sodium, you're going to get 20 grams of output, right? But when you're dealing with the atom, you're breaking atoms apart, and you're forming new atoms, and you're releasing the energy equal to the mass of the two atoms that have combined together, the delta of that multiplied by the speed of light squared, which is 16 zeros. So you're talking about like a sugar packet worth of fuel generating millions of volts of electricity.
Okay, and so I read your blog that you had on your LinkedIn, and your premise is you can put fusion reactors pretty much anywhere because they're not using radioactive material, so they're safer from that standpoint and subject to less regulation.
Well,
right?
All fusion reactors that are currently being contemplated in the United States are going to be governed under a separate rule according to Congress, which was passed last year, separate than what fission reactors are going to be governed by. So we're going to be treated like the kind of like a radioactive medicine. So the deuterium and tritium guys have to have neutron shielding, they have to have certain restrictions because they are dealing with radioactive material and they have radioactive waste. The proton boron guys like TAE, we don't have those restrictions. So we could put a TAE nuclear fusion plant right here at the stock exchange, or the bottom of the Citibank building.
So you hear about these modular fission systems, and they're out there. They're in China and other parts of the world. But your point is that they emit nuclear waste, radioactive waste, and you have to do something with that. So you have to store it for thousands of years.
We
right?
we have decades of history with small modular reactors. I mean, really every U.S. nuclear submarine or ship has effectively a small modular reactor on it.
Right.
The challenge is you're dealing with, weapons grade materials in terms of uranium, plutonium as your fuel. And then you have a waste stream that comes out of it. You have to store that because it lasts for millions of years. It's still radioactive. It has to be stored very, very carefully. And depending on what your fission reactor is, you could be creating materials that can be used for weapons. And so you don't want to support nuclear proliferation, right? Fusion doesn't have those problems. Even the tritium community is really not going to be the half-life of tritium is 12.3 years.
Okay.
It's not a million years, right? So it's a big difference. So whatever fusion solution we come up with first is the best energy option for the planet.
Now let me ask you a question. Given, my understanding is with fusion, you're heating up the elements massively. Over time, could that create radioactive material, and how do you deal with that?
Well, let's kind of explain how it works. So if you look at our sun, it's in a vacuum, which we call space. There's a tremendous amount of fuel. It's a million times the size of the planet Earth, right? And it's full of hydrogen and helium,
right,
primarily. It's 98.6% of all the matter in our solar system. So that's how big our sun is, right? It's a good thing it's 93 million miles away because we'd be baked, right? So all of that mass forms a great deal of gravity. That gravity pulls these atoms together and forces them to fuse. So it's the heat and the energy of that it makes the hydrogen fuse with hydrogen forming helium, and then all that light and heat and energy is just sent off into space. So what we have to do is replicate that. And we don't have the mass of the sun. So the core of the sun is 15 million degrees C. In order to fuse deuterium and tritium on the planet, we need 150 million degrees C. In order to fuse boron and hydrogen, we need 1 billion to 1.5 billion degrees C. So as soon as you start putting these numbers out there, people's heads explode.
Yeah.
Because they're like, wait a minute, how can you possibly fathom temperatures at this level? Because there's no material on Earth that can, or in the universe, that can deal with a solid material that could deal with 1,000,000 degrees C, let alone 150, right? Well, gases can, right? Superheated gases become plasma,
Right.
which is what we're dealing with. We're dealing with a plasma, which is a superheated gas, and it's a gas made of either hydrogen or boron or deuterium or helium. And once it gets hot enough and energetic enough, we create the conditions like the sun that allow these atoms to fuse and merge and create a tremendous amount of energy.
It's blown my mind that we used to talk about backup software, and now we're talking about this topic. Talk to me about the economics and the comparative economics between fusion and fission.
I could speak really well about the economics for proton boron because boron's mined by the metric ton, it's pennies a pound. The average natural gas combined cycle plant, 40% of OpEx up and down based on the cost of gas is operating expense. That's your cost of fuel. In the case of a boron fusion plant, your cost of fuel will be less than 1% of your operating budget.
And you don't have to store the radioactive waste either.
Well, and again,
that's got to be a big expense for
you don't
fission.
have radioactive waste. But just to be absolutely crystal clear, having an entirely pure vacuum where the only thing that goes into it is hydrogen and boron is a virtual impossibility. So there could be other materials in there that may end up fusing and becoming neutrons. So there's going to be light shielding in that type of machine. And every once in a while you open it up and sweep the dust out and put it in a paint can and bury it in the parking lot for 10 or 12 years. That's going to be it. But with tritium, you've got to take that stuff out, and the materials it infects, and you have to bury that for 12 and a half years or 25 years. You really want to be careful. So it's a very, very different waste stream situation than you have with fission. And because it's not a chain reaction, there's zero chance of meltdown or explosion.
Right.
What makes fusion so hard is what makes it so safe. If you break a fusion vessel in half because you have an earthquake or an explosion, it just goes out. The vacuum escapes, the plasma gets cold, it just stops working.
Where are we in terms of the timeline for fusion? I mean, fission, as I said, I believe, correct me if I'm wrong, but there are plants today, small modular plants today, that are doing nuclear fission.
There are small modular plants in the military parlance, but there's really no modern SMR reactors operating in the United States yet today.
No, but there are in China, are there not?
Yes. So there's a regulatory hurdle that the SMRs have to go through with the NRC.
Right.
That can sometimes take up to 10 years. So they're trying to accelerate that. But there are SMR programs underway in the United States. But I would tell you that the time frame for new SMR technology to come online and for fusion to come online is probably neck and neck.
What is that time frame?
Within the next 10 years. And
so mid 2030s.
I would say early 2030s is what we're shooting for. There's a very heated race going on between TAE and other companies. Our next machine will prove more energy out than in, which is...
Okay, so that's a huge milestone.
That's the hurdle. Once you can, take a megawatt in and put 10 megawatts out, then you're in good shape, right?
Think we can get there with our debt?
I wish we could.
So, okay, now when...
Well, we could, by the way, it's germane because when you have an energy source which is not restricted by access to fuel, which does not produce any harmful pollutants or radiation, then, and it's super low cost because you can scale it out because it's the energy of choice. Total factor productivity, how we build goods in this country, includes energy as an input.
Sure.
When that cost of energy comes down to nil, our productivity goes up, and the energy is going to be used to power this next generation of AI chips and learning and software, which is going to double, if not even quintuple, U.S. productivity. So that's how we're going to deal with debt.
What's the starting story, the startup story of TAE? When was it formed?
TAE was formed in 1998.
Amazing.
A long time ago, and I actually invested in the company. I was in private equity at Pequot Capital at the end of 1999. So I've been an investor in the company for just about over 25 years.
How did the company convince you to do, I mean, you knew at the time it was going to take decades, right? But as an investor, you were looking at many, many decades before you saw a return.
Well, I guess I did not get involved in TAE officially as a Pequot investor because I brought the opportunity to investment committee, of which I was a member.
Right.
And we reviewed the thing and they said, Jim, you're insane. This is never going to happen. And the horizon that we needed to, 7-year return, not going to happen. I said, you're right, it's not going to happen. Like, what are you doing then? I said, well, I need you to reject it so I can invest in it personally, which is what I did. And then 1, 2, 3, 4, 5 of my partners in subsequent rounds invested in the company as well, including Art Sandberg, who was the CEO and founder of Pequot Capital. So we got into it for the reason that the planet needs it. So I think it was as much altruistic as it was hopeful that there could be a really high beta here, right?
Right.
But now the investors we're talking to can see the 7-year horizon.
Oh, now's the time to get in.
Now's the time to get in.
I mean,
we've spent $1.4 billion getting to this point, which is, I think, a really good stewardship of capital for 25 years.
$1.4 billion since 1990, the late 90s. That's not a lot of capital.
I mean, we've not a lot of capital, but we've built 5 national lab scale machines. The last machine we have operating now is operating at 75 million degrees C and containing plasma stable for up to 40 milliseconds. The next machine is going to 150 million degrees C, where we'll have the conditions to prove net energy out. And so that's scheduled to be commissioned and operating in 2028.
This decade, okay, so that's a huge milestone.
And then our next machine right after that is our first commercial prototype, which will push 50 megawatts of power to the grid.
And then a couple years after that,
that machine's called Da Vinci. And I happen to think that once Copernicus is proven in 28, we're going to have so much interest, we're going to run the prototype program and the commercial program in parallel. So TAE Fusion 1 is designed as a 350 megawatt power plant. And so you'll put a couple of those next to a gigawatt data, AI data center.
Right.
And you'll just go off to the races.
So, I'm glad you brought up AI, because that's what, the big gate to AI is energy.
Yeah.
So, what are the conversations like with all these AI players or the government? Is it too premature? I mean, they know it's coming and it's like, call us when you're ready. What are those conversations like?
The biggest change in the fusion space, other than fusion progress and milestones and all those things, which has been really successful, has been the attitude and the demand in terms of go-to-market. So, 20 years ago, obviously, we're thinking, okay, we have to work with utilities, we have to connect to the grid, we got to coexist with an old coal plant or a gas plant, and that's a very cumbersome and challenging path to go down. Utilities are risk adverse, grid interconnects are complicated, regulatory issues are high. Now what you have is single public companies that have energy budgets in the terawatts.
Yeah.
The demand for AI is going to very quickly exceed the total consumption of energy for the nation of Japan. So you really can't continue to adhere to your net zero promises to your shareholders of 2030 or 2040, depending on whether you're Microsoft, Amazon, Meta, or Google, right? They have different promises.
They're all struggling with it.
They all need to kind of keep that promise on the table and to be able to do it with gigawatts of power on demand. The problem with wind and solar is they're not dispatchable. They're not available 100% of the time. So you need to have dispatchable power. Nuclear fission and nuclear fusion are the highest capacity dispatchable solutions you can hope for.
So it makes the economics much more attractive.
Makes the economics much more attractive.
Notwithstanding the radioactive component of fission.
Yeah. Well, there are, look at, Microsoft bought 3 Mile Island.
Yeah.
They're recommissioning, one of the reactors to provide power for Azure, for the Microsoft Cloud. There are a number of data centers that are, sitting parked next to nuclear power plants or hydro plants. When you have the ability to start putting down 350 or 500 megawatt plants wherever you need it, this whole thing is going to change. So what I guess what I was saying is, we're no longer too worried about convincing a utility to take a chance. We now have a number of hyperscalers who say, if you can deliver power under these requirements, we'll buy it. and we'll buy it many times over.
Now, you mentioned earlier that the regulatory constraints are much less for fusion than they are for fission. What are those constraints to the extent that they exist? What is the regulatory environment like for fusion?
It's the same restrictions that you put on medical facilities that are dealing with radioactive isotopes. So you've got Memorial Sloan Kettering here, you get NYU Langone, you know, people come in for radiation therapies all the time. You know, those types of careful security, you know, precautions are in place. So the bigger risk in having a fusion plant from TAE is the fact that within our building, we're dealing with millions of volts of electricity, you know. So it's really an OSHA, you know, kind of how do we manage storing and dropping a gigawatt of power in a couple of milliseconds without anybody getting hurt.
Employee safety, yeah.
You know, it's all employee safety. And we've been doing this for 25 years. So we have an excellent safety record. We know what we have to do to build a safe power plant. And because we don't have the same radioactive footprint that other fusion parties or fission parties have, I think we have a significant advantage.
That's probably a primary metric that you guys track, employee safety.
Our fuel costs are negligible. Our radioactive waste is negligible.
Yeah.
You know, it's all carbon free. So, you know, you're going to start seeing generation 1 with levelized cost of energy numbers in the 7 to 9 cents a kilowatt. And this is not taking the benefit of carbon credits, for instance, because this is carbon-free power, right?
Yeah.
So that's Gen 1. But when you get to Gen 2 and Gen 3, and you and I have been in the tech business for a long time to know
we
how
know the
technology
delta
evolves, it moves really fast. You know, you're going to see, you know, things below 5 cents a kilowatt hour very, very quickly. That's my goal.
Amazing. And then where are you guys in your capital raise now? You've said you've raised at 1.4 billion?
We've raised 1.4. We have a round that will be closing soon, and then we have another round on the back of that for funding the entire operations of Copernicus. But it'll be news to come in the near
what
future.
What do you use that capital for? You're not buying GPUs like a lot of companies.
No, well, we do have GPUs because we do a lot of AI.
Yeah, okay.
You know, we did.
But that's not a constraint for you, right?
It's not a constraint. We did a deal with Google a while back. They're an investor in the company, but most importantly, they also invested services in kind, and so we did a lot of ML development, AI development.
Okay.
We developed something called the optometrist algorithm, which basically looks at hundreds of thousands of plasma shots and says, if I have these conditions at this point in time, what do I have to do to make the plasma more stable, or move it this way or move it that way, make it long, make it short. So we have an AI process that's actually running the machine when we're operating plasma. And we developed that with Google. We have Chevron as an investor, we have Sumitomo, we have just a whole bunch of interesting parties involved, yeah.
And what do you use that capital for? What are the big?
Well, it's building machines. It's really hardcore R&D. I mean,
so it's a capex and it's the people.
It's exactly. It's buying equipment, you know, handling our supply chain, building stuff, paying payroll, and you know, to that end, we've created 2 other divisions which can bring product to market faster. We have TAE Power Solutions, which is in battery storage and electric vehicle drivetrains, and we have TAE Life Sciences, which is using our particle beam technology to treat and cure cancer.
Are those revenue producing? Or?
Yeah.
Oh, they are. Oh,
yeah.
okay. So you have a revenue stream.
We have, those 2 divisions have a revenue stream, but it's very early days.
Okay.
Yeah.
So we're talking about Ray Kurzweil on the way in. When do you think reality is going to outstrip sci-fi? I think we'll see that. With all this power you're going to hand us.
You know me, I've been a tech nerd, you know, my whole career, and I remember when the internet was coming on, and I was like so excited about getting connectivity around the world and opening up doors for people who didn't have access to information.
Yeah, we all were. It was amazing.
And what that was going to make, you know, possible for all of us, and we lived through that together. And now, when I look at the strides that AI is making on a daily basis,
it's absolutely
completely mind-blowing. There's a study I read today that the average worker can get, you know, a given task done in half the time, and with a 20%, you know, better output. You know, I use it all the time, you know, for things that I do, and it's just early days. So I think we're looking at tremendous labor disruption in our country. I think that everybody needs to get educated on how AI works in their space and how they become the purveyors of AI technology as opposed to the individuals that are going to be replaced by it. And
well,
I think that's really
I'll
important.
ask you, because you got a long perspective and a good perspective on this. Everybody, so much in the media is the negative of AI. We heard the vice president in Europe talking about the positives, which was good. I was happy to hear that. But it's interesting, the whole jobs discussion. I've talked to so many leaders who have said, yeah, we're not really using AI to cut people. I mean, some organizations are. I actually think some of the layoffs, they say AI, but it's not necessarily directly related. But here's the thing, Jim, and I'd love to get your feedback on this. You're alluding to new waves always create new opportunities. And if you use the tools properly, you're going to create new jobs. But for the first time in history, we're replacing cognitive work with machines. I mean, machines have always replaced humans, but never for cognitive work. And that's a different, it's kind of a curveball on the traditional pattern of creating jobs. What do you think about that?
I think that it's going to be a good deal of time. I mean, look, an AGI is not going to be capable of real human creativity. It's going to be capable of tremendous mimicry and the ability to copy what humans are capable of. And it'll write a hit song that you probably couldn't tell from, a real artist, and it'll do things of that nature. It'll create art. We're already seeing, Christie's saying that they're going to sell AI art. They're already doing it. There's going to be disruption. But like anything else, all the tools that you and I have used in our careers have been amplifiers. They've been ways in which we can be more productive and get more stuff done and do so in a better way, right? So I think applied correctly, AI is going to increase productivity. We're going to have a much higher GDP in this country. You brought up our debt situation. Lord knows we've got to grow domestic product if we're going to have any chance of bringing down debt. And I think the other real gauging item here is AI doesn't happen without energy. And for all of the history of this planet, energy has been extracting and cutting down. We're either cutting down trees and burning them, or we're drilling for oil and burning it, and we're changing our climate as a result of it. For the first time, other than fission, and fission didn't go at scale because of the risks associated with it, right? We could have had fission operating at scale, and we could have figured out a better way to deal with the waste, but we didn't do it. Everyone got a little bit shy, and it slowed down greatly, right? We have 70 new fission plants currently on the schedule to be brought online in the next 10 or 20 years. Right. But what happens if we bring on 700 or 1,000 fusion plants? 80% of the energy produced in the world is produced by fossil fuels. 54% of the energy is consumed by industry, and most of it in the form of heat. So if I could take off half of that, replace all the industrial processes with fusion plants and power all the AI stuff and do it for pennies a kilowatt, what does that do to productivity? What does that do to AI? What does that do to building robots and putting robots to work, right? I think that we have an opportunity to build a civilization and an economy that leverages automation, that leverages robotics, that leverages AI. It would make a very promising future for us. Putting our heads in the sand like the Luddites did when the steam loom came online doesn't work. I don't know any elevator operators anymore. You don't know any VPs of electricity anymore. We don't know any buggy whip manufacturers anymore. We have a really good history of being able to adapt to change in new technology.
Yeah. So drill, baby, drill, fine. Drill, baby, drill, but that's not going to be a game changer. It's not going to provide a step function like what you just described.
Well, and it's a finite resource. Yeah. I mean, depending on who you talk to, we have oil reserves of 50 or 100 years.
There's only so much oil in the ground.
There's only so much oil there. So the sooner we can, replace that, as an energy source and use it for other things that oil are really good for, that's great, right?
Do you follow quantum at all? I'd love to get your thoughts on
quantum
this.
Computing?
We've had some folks in here that say, hey, we're going to solve the AI energy problem because quantum doesn't take that much energy. I don't know if you look at it at all, or as a technologist. Or
well, think about it. Well, I mean, quantum is I understand fusion. Quantum still blows my mind. I mean, It's a 1, 0, or maybe something else.
Right.
It's here, there, and it's also way over there.
Well, the reason I bring it up is because, Jensen says quantum is, 10 plus years away, 20 years away. And then we had, and just in here, we had a CEO of D-Wave saying, no, we're shipping this stuff today. It's just, a lot of confusion out there in the marketplace.
Look, I think quantum, I'm more concerned about quantum breaking all the cryptography
Security,
out
yeah.
there. What's going to happen to Bitcoin, when quantum gets a hold of, solving blockchain problems. I think that, think about quantum the way I think about the latest DeepSeek, market crisis, right? The DeepSeek, model came out and it was built for, a tenth of the amount of money, and it was super efficient. It did a really good job, and the whole market went down. NVIDIA dropped 18%.
But didn't you think that was like crazy?
It was crazy.
DeepSeek is a good thing, right?
And it's basically, I grew up as a software engineer, and I was always desperate for the next chip.
Yeah.
What can we do with the 286, the 386, the 68,000, up to the Pentium, all the way up to today. And NVIDIA's come out with the Blackwell. There's not a single AI engineer out there who says, give me last year's chip.
I don't want the old stuff, right?
I want the old stuff, right? No, they'll take the Blackwell, and then they'll put DeepSeek algorithms on it, and then they'll go faster. So if a quantum computer were available to basically write code that is AI friendly code, which is not entirely clear to me yet. I mean, the quantum brains could probably figure it out, but GPUs and vector math is really good for AI. I'm not so sure how quantum does it, but they'll figure it out. I think it's amazing.
Yeah, it is amazing.
Yeah.
Yeah, so Jim, I love having you here. It's really a pleasure to reconnect with you. Thanks so much for coming in and sharing the future of energy, and congratulations on getting this far, and good luck in the future.
Thank you very much, David.
Great
Always
to see
a pleasure to see you.
Thank you. All right, and thank you for watching. This is Dave Vellante for theCUBE. Keep it right there for more great action from NYSE.